Okay, welcome back. I am going to deliver a online lecture for October 13 on the cosmology class. Okay, so I'm sure that because of this long break, you may not be able to remember all the stuff that we discussed, but I'm hoping that we have these three equations that you probably want to uh, remember throughout the at least semester because they are the important. The first one is called the Friedman equation. This is the differential equation of describing the expansion, or in principle the counterpart of the expansion shrink of the universe depending on the density and curvature. So we need to know the density and curvature. And to know that, we have to have independently another equation, which we call it fluid equation. So this is, again, the differential equation containing time derivative of energy density, as you see here, and as well as time derivative on the scale factor and the pressure. And this is for only one component of the energy. And as we will discuss, for the multi-component universe, we have to consider several of them. And the third one is called the acceleration equation because it contains second derivative on the scale factor. And as we discussed in the previous class, this is sort of was derived using first two equations. So the third one is not independent from the first two, but sometimes it's useful. So first bullet, already I mentioned it, and we have basically three unknowns, maybe four, because, well, R0 is a constant or infinite if you assume flat universe. But anyhow, we have scale factor, energy density, and pressure as a function of time. They are not given to this model. One has to find out. And then we need what's called the equation of state. That's the subject of today. And what do we mean by equation of state? It's a relationship between the pressure and the energy density. That's what we mean by equations of state. All right, next. All right, so we want to talk about equations of state in cosmology. Fortunately, in our case of cosmology, this is very simple. Pressure is a constant, which we call W, and we call it as equation of state parameter times energy density. So W is dimensionless because as far as the units are concerned, the pressure and the energy density, they have same units. You should be able to check my statement here. But in general, if you are working on the condensed matter physics, this is huge topic and it's very complicated function. But for us, this is very in the cosmology, this is very simple, like this. So we want to discuss this equation of state parameter for various state of energy densities. And the first one is so-called non-relativistic massive particles. We think about a gas of such particles. So its density is fairly low, at least that's the assumption anyway. We are saying that such a non-relativistic gas follows the ideal gas law that we, I suppose, may have heard in high school or in first year of chemistry. I hope you learned chemistry, general chemistry or something, or even in high school. Anyhow, the pressure is proportional to the temperature with a certain constant, which we call Boltzmann constant, and it has it needs information about down to the mass of individual particles. Rho is the density and mu is the mean mass of the gas particle. So you can consider energy density is mass density times speed of light square because it's non-relativistic. So you can write down the pressure is whole is constant, not constant, temperature is in, times energy density. So whatever this is should be corresponding to equation of state parameter. So now let's calculate this. So we have information, I think this is also from general physics. We can relate the temperature of a particle in the system and the velocity as 3 kt because of 3 degrees of freedom, mu, and average velocity square. And if you are not familiar with this, perhaps you can go back and take a look at the general physics textbook. So we can relate the term, let's go back, this term to v square divided by 3c square, and energy density, right now we put non-rel, saying that this is the energy density for non-relativistic case. So density of state parameter for equation of state is basically corresponding to this. So it's non-relativistic. So the v square on the average normalized by speed of light square is basically very, very small. And later on we will put 0 in, and that's a good approximation. And as we will discuss in cosmology, protons and electrons were non-relativistic in most of the history of the universe, unless we are talking about very, very, very early universe. And we will come back to that. Now we want to talk about photons as well as neutrinos. And they are so-called relativistic particles, meaning the speed is very close to speed of light, and for the photon it is the speed of light. And to get the equation of state parameter for this system, we consider this cubic box with the each length to be L. And let's assume photons and neutrinos are in this volume of the box. And then we think about a photon moves left and right after colliding at both ends of the small wall of the area. So photons are hitting the wall and bounce back. And we say F is the force delivered to the wall, and P is the momentum of the photon, and C, of course, is the speed of light. So force is, that's a little confusing, but the force is momentum change divided by time change. So momentum change is it's an elastic scattering of the photon and bouncing back. So the change of the momentum is 2 times p divided by time scale is 2L normalized by speed of light, giving you pc over L. Pc is in relativistic formulation is equal to energy normalized by the length. The capital P, which is the pressure, so don't be confused with the little p. Little p is the momentum, capital P is the pressure. Pressure is by definition the force per area. And F is E over L, so energy normalized by LA. LA is the volume, so P is the energy density. And one thing we have to be careful is this sort of argument was based on only one-dimensional case. And we have two more degree of freedoms, x, y, z. So we have to have this factor 3. Therefore, the equation of state parameter for photon is 1 over 3, which I thought I promised to prove in a previous case. So let's summarize the classification of equation of state parameters. When omega is close to be 0, we call that to be matter component or non-relativistic. Stars, the earth, sun, gas in interstellar space, all this non-relativistic matter, including dark matter that we will discuss much later. And when omega is 1/3, it's a radiation, including photons and neutrinos. And when omega is less than negative 1/3, we call that to be dark energy. We want to talk about that later on. And in the case when omega is -1, we specifically called that form of matter to be cosmological constant. So it's a subset of dark energy if you take a look at the definition of these two. So next topic is related with lambda, the cosmological constant lambda that was proposed by Einstein for the first time. And the textbook author is saying that we have to learn how to love lambda because it's important. So a little bit of history. And in 1920s, the universe was known to be static. There's no indication whatsoever. So Einstein, actually Friedman discovered Einstein's theory allows dynamic solution on the universe. So Einstein modified his equation of general relativity to explain the static universe. So he put a term called the lambda. This is a kind of, as we will learn, the universal repulsion that prevents a uniform distribution of matter from collapsing. You can imagine easily, if you have stuff in the space and you have gravity, so eventually things will move around and maybe collapse. So static universe cannot exist unless you have some sort of the energy form that forces not to gather around. So that's the rough concept of the lambda. And let's start with the Newtonian context. If you start with gravitational potential phi, and normally we don't do it, but it's the same thing as Coulomb force, so we can get the Poisson equation about the gravitational potential, which is equal to constant times the mass density. And you can also get the acceleration due to the gravitation is equal to gradient of gravitational potential with negative sign in general. But for static universe, you shouldn't have the non-zero A, because if you want to have non-zero acceleration, things will move around. So one thing is, for rho being from the first equation, it's constant times a Laplacian phi, and you ask this to be 0. And one way is to realize is to put a constant term, lambda. And that's what Einstein did, but not with Newtonian mechanics, but It's a sort of educational purpose. And before we go into Friedman equation, I'd like to show this concept. This cosmological concept is a bit strange because if you plot the density of energy states as a function of scale factor, so as universe expands, the scale factor increases. And you can think about the density of radiation. It will decrease, and it decreases faster than rho m, which is the density of normal matter. So normal matter density will decrease proportional to a power of -3, because that's the volume, inverse of the volume. But in the case of radiation, the dependence is a -4. It's a detail, but we will come back to that. But rho lambda, energy density of cosmological constant, is flat. So even if your volume increases, you have to, in a sense, you have to create this dark energy to have dark energy density to be constant. So that's quite strange. But anyhow, let's go back to the Friedman equation. And so Einstein actually put another term, lambda. And for numerical purpose, lambda over 3 was put in this equation. And fluid equation is there. But the acceleration equation, which combines these two, will have lambda over 3 if you derive the acceleration equation from the scratch, as we did in the previous time, with this new Friedman equation. Then you will have this term. And then you can put that back, this lambda over 3, in this epsilon energy density as the second term, or maybe not second, another term should exist in universe. So you can introduce energy density of lambda to be this numerical vector times original term lambda to make dimension correct. And if you did that, did I go 8, 9? Okay. So you can have this epsilon lambda in, and note that from the fluid equation, the lambda term has an association with the pressure because epsilon lambda is a constant. And epsilon lambda is time derivative is 0 plus 3a dot over a, epsilon lambda plus p lambda is 0. Remember that the fluid equation has to be satisfied for each component of the energy density. And we are evaluating energy density for cosmological constant. And because this is constant, we have this simple relation. Pressure is negative of energy density of cosmological constant. So first of all, pressure is negative. A little strange concept. It's constant negative pressure. Now let's consider a universe with matter density rho and cosmological constant lambda. And for that universe to be static, we require the acceleration and expansion also must be 0. So if that's the case, the acceleration equation becomes, this is 0, we have 4 pi g over 3 minus rho plus lambda over 3 is 0. So we are getting lambda is 4 pi g rho. That was the result from the Newtonian case. So that's what we learned from the acceleration equation. And if you if we use a dot is equal to 0 in the free body equation, the left hand side is 0. This is what we get. And then we have 4 pi g rho minus the curvature term. So Einstein's static model had to have the positively curved with the radius of the curvature. R0 is equal to this value, which is c over square root of lambda. But it's unstable. If your Einstein's universe was perturbed somehow to be expanded a little bit, then lambda remains unchanged by definition, but energy density drops. Therefore, repulsion force becomes greater than attractive gravitational force, and then universe will expand further, so it's unstable. So that was abandoned, thrown out after the discovery of the Hubble, because Hubble found out actually universe expands, and the community agreed on the fact that we don't need this cosmological constant. But suddenly it came back with the accelerating universe of today. People recently found out our universe is actually accelerating in the expansion. So that actually more than 10 years ago, a Nobel Prize was given to I forgot, one of them is Rice, and this is the plot. So the vertical is little funny unit. It's a mass, magnitude, but I will explain later, actually much later. And then as a function of a redshift. So as you, for larger redshift, you are looking at the object that is farther away in universe. So there are various lines, and the best fit, which is this thick line. So this is certain measure that is related with the expansion, which I will explain later, as a function of z in the log scale. And the bottom one is delta, so it's a sort of difference between the data to fit. So it's easier to see this. So best fit, best parameter that explains the data is this curve, where you have matter component to be 0.2 and dark energy component to be 0.8. So major component of the energy is actually dark energy as of today. And there's no room for the others, curvature. So according to this, the universe seems to be fairly flat. So that's how we interpret this plot. So the cosmological constant came back, and people call that to be dark energy. So it's an energy form that we don't know what it is. We call it as dark matter because we don't know. So people seem to use the term dark whenever you don't know what it is. So dark energy is some energy form that is driving the accelerating expansion of the universe today. I emphasize today. And later on we'll talk about inflation, which is a scenario at very early universe. So it's nothing to do with the inflation. And the short answer is we do not know what it is. Just like dark matter. We have indirect indication of dark matter, but we don't know what it is. And the leading candidate for dark energy is called vacuum fluctuation. That has to do with quantum mechanics. For dark matter, we have several candidates that explains a lot of observed quantities, but for dark energy, it's very we don't know nothing about it. So the reason is the leading candidate is called vacuum fluctuation, but it has a big problem. So I hope all of you took the quantum mechanics at least, otherwise it's not easy to follow what I am going to say. Suppose you have a photon in vacuum, so photon flies in, but in quantum mechanics, there's a non-zero probability that photon is annihilated to create one electron and one positron, anti-electron, and then one pair of electron positron will annihilate, emitting photon. Such a process has non-zero amplitude, and in quantum mechanics, if there is a non-zero amplitude, that will happen with potentially smaller probability. And you can keep argue this way. You can come up with more complicated decay method and so on. This diagram is called, by the way, Feynman diagram, that it has been used actively in particle physics, and this is a symbolic way to describe how interactions are formulated in graphics. So one can add all of them together. So meaning, whenever you say vacuum, it's not nothing. It's full with this interaction. So you can calculate the energy density of all of these interactions. And rough estimate of the vacuum energy density is to calculate using Planck energy normalized by Planck volume. This was something that we discussed in the very beginning of this semester. And then you realize that the energy density of vacuum is in units of electron volt per cubic meter. It's a very large, 10 power of 132. That's the problem. Because if you convert the observed dark energy density in the unit of electron volt per cubic meter, it's only 10 to the power of 9. So you have this difference on the order of 10 to 123. And no one believes if your theory is wrong by this amount. What does it mean? We have no idea what dark matter is. So that's the situation of understanding on dark energy at this moment. And if you have a better idea to explain it, then that'll be great. Okay, that's all I prepared so far. And from next class, we will discuss the actual evolution of the universe with Friedman equations. Okay, thank you. Bye-bye.